can go ahead and get started. So thanks everybody for joining us. Our speaker today is our special guest, Ezequiel Treister, who's normally a professor in Chile, in Santiago, at Pontifical. I don't actually know how it's translated in English.
I don't know if we translated Catholic Pontifical University. Catholic University.
Yeah. Anyway, the Pope's University in Santiago. That's who owns that place. But this semester, he's actually on sabbatical at NRA in Charlottesville, which is why we get to have him here. It's a little bit of a shorter journey. So he got his PhD at Yale, learning X-ray astronomy from Meg Urey, and since then he decided that he wanted more photons. So many more photons now. Today he's going to tell us a lot about his work understanding AGN and galaxy evolution. So, all right, thanks.
Thank you very much. Thank you, Justin, for the invitation. It's really a pleasure to be here visiting for the first time. So very exciting. And to tell you a little bit about my research and yet what I've been doing, and yet this transition from counting photons in X-rays to doing interferometry with alpha. And I will get to talk a little bit about what. But fundamentally, what I want to talk about and what I've been working for years now is trying to understand how black holes grow. Essentially, we now know that we have these supermassive black holes that live in the center of galaxies, that for many years we thought they were just a space oddity. So they were cool, but not really interesting. And now there's another fundamental piece of galaxy evolution that we need to understand, and in particular, how black holes grow and get their masses now become a fundamental astrophysical question. So that's basically what I've been working on, and a little bit of what I will be talking about this morning. Now, hopefully I don't need that much motivation, but it's really a good time to study black holes now. The last 2 years were very exciting. We at least half the 2020 Nobel Prize in Physics went to study of black holes, more specifically about the supermassive black hole in the galactic center, which you can, it's still the only place where you can actually trace individual stars moving at velocities of 3,000 kilometers per second around a supermassive black hole, and then you can do Keplerian dynamics and determine their orbits and hence measure their mass, and you end up with a very well-defined, very precise measurement of the mass in the center of the Milky Way, and you get something like 4 million solar masses. Now, of course, it got a lot more exciting in the last year when people were able to, with the EHT, were able to take pictures like that, which actually show what is happening around the black hole, not exactly on the black hole itself, but in the surroundings of the black hole, or in the same black hole in the center of the Milky Way, but also in nearby galaxies. In this case, in 87, with a black hole that is about 1,000 times more massive than the one in the Milky Way. But people are starting to do that. So definitely in the last few years have been very exciting to study black holes. And again, the point I wanted to make is that other than studying black hole, which is interesting per se, and from the physical point of view, it draws all sort of interesting questions and all that. It's really a fundamental ingredient for galaxy evolution. So basically, it's clear now, and it's been clear for the last 2 decades, that if we really want to understand how galaxies form and evolve, you also need to care about what the galaxy in the center, the black hole in the center is doing. And why do we believe that? It's because, well, first we know it locally. I was just showing about the black hole in the center of the Milky Way, but also we know that the Milky Way is not unusual in that sense. We don't live in a weird galaxy because it has a black hole in the center, but actually all, or at least the most massive galaxies, and actually whether there's a limit to what galaxies can host black holes, but at least the most massive galaxies have central black holes in the center. I show a couple of examples. Great, there are people here working that have done amazing work, first doing optical spectroscopy, but also now using ALMA. Turns out ALMA, which I'm going to talk about, as Justin was saying, now I'm mostly doing ALMA. Turns out ALMA is great to measure black hole masses as well. So when you do that, you realize that again, all or at least the most massive galaxies have supermassive black holes in their center. But this is not really breaking news, but we now know that the galaxies don't just have any black hole, but they have a black hole that corresponds to the galaxy in some weird and fundamental way, and that the mass of the central black hole is connected to galaxy properties. And I know people that have been working, including people in the audience, have been working on that for many years, but here's just one example of the so-called M-sigma relation, which you can draw. You can use many other ones, and you can and end up spending an entire talk or more, or have a conference on all these possible correlations and different ways to compute it and which one is more fundamental than other. But essentially, no matter how you do it, you end up with a connection between the properties of the galaxy as a whole and the property of the black hole in the center in a non-trivial way, which we are in the process of understanding how this connection takes place. And hopefully a little bit of what I will talk about today will cover a little bit of that. And then finally, when you make a black hole grow, you emit a lot of energy. And again, we can debate, and people debate how much goes into kinetic energy, how much goes into radiation, and how much radiation and what wavelengths, which actually I'm going to talk about in a second. But no matter how you do it, the energy output from a growing supermassive black hole can be important for galaxy evolution. And actually a fundamental question is how important it is. And it's not obvious at all, because it turns out that the link, how do you connect the energy output, the luminosity output from the material that is being accreted by the black hole and the surrounding environment is a fundamental question, and people have been trying to do that for many years. And again, this can be an entire different talk, which I'm not going to do because I'm not the right person to do it. But essentially, people have been doing mostly with simulations, but you can put you can include this the energy output from the black hole into the environment, and it will do fundamental things. You have the ISM, or you can get rid of the gas in the galaxy, and then you can either shut down star formation. You can also trigger more star formation, or both at different times. Anyway, it's an entirely different process. But no matter what, the point is that, again, if you care about galaxy evolution, you need to care about the black hole growth as well. You need to include that, otherwise it just doesn't work. And that's something that now I have been saying was controversial for many years. I don't think it is anymore. So then the question is, how do black holes grow? How do black holes grow? How do they get their masses? And essentially, the more or less do it in systems like that, which, again, as Justin reminded us, I did my PhD with Meg, so I'm still legally obliged to show this picture. She doesn't charge me copyright, but I do need to share. And again, entire conferences related to this, and whether these are the right ingredients or the right geometry or something. But the fundamental point that I wanted to make is that sort of these are the key ingredients that you always have when you have a growing black hole. Right? Obviously, you need to have the black hole in the center. You need to have some accretion disk. We do see properties. We have several properties. We know that the material before being accreted is in this accretion disk. That is on relatively, it's definitely in subparsec scales around the black hole. And we need some reservoir of material where essentially the gas in all these phases is stored or is reserved before eventually feed the black hole. And again, I'm not going to get into the geometry and the different aspects, but this was the original claim a long time ago, and it's probably still more or less correct. In fact, at least some of these, in some sufficient degrees, all these ingredients are there when you have a growing black hole, and they're all important. Now, another consequence of that is that this, in many ways, determines what we see when we have a growing black hole, which, again, is something that has been debated and discussed for many years. Now, we have a very good idea of what a galaxy hosting a growing black hole looks like. And essentially, one of the fundamental properties, which I find very, very appealing, of this system, this AGN, this Active Galactic Nuclei, is that they emit at a very broad range of wavelengths, as opposed to more typical normal galaxies, which they get most of the emission in the optical, near infrared, and some degrees, depending on blast and so on. AGNs emit at all wavelengths from radio all the way to essentially gamma rays. And again, different amounts. And depending on the geometry and depending on the contrast or the ratio between the amount of black hole growth and the host galaxy is what we see. And I really like this. This comes from a review by Brian Hickox and Dave Alexander, which I think summarized this very well. A lot easier to do. Normally I would spend 10 slides and now I can show this diagram. So this is great. So essentially what we have here is changing the ratio of the AGN to the host galaxy, right? Which in a way is controlled obviously by the AGN luminosity, which in turn is related to the black hole accretion rate. On the other hand, but I will talk about it in a second, but you also change the obscuration, the amount of obscuration that you put in the system, which is related to what I was showing in the previous slide, at least in the classic unification paradigm. It's essentially related to the line of sight, which we are looking at this instead. Now, in the second part of my talk, I will argue that is more complicated than that, but we'll get to that later. But essentially, those two, let's say, parameters determine what the CD, the spectral shape of an AGN will look like. And again, they emit at all regions, in this case, showing from mid-infrared to hard X-rays. And you can see that as you increase the contribution from the AGN, you outshine the host galaxy. You start to see also the images here represent more or less what we see. So we start to see something that looks more like a point source, essentially unresolved emission from the nuclear region. As the contrast increases, of course, you get more like a normal galaxy as well. And also depending on wavelength, you get different effects from the obscuration. So essentially the emission coming from the accretion disk, mostly in the optical and the UV, is significantly affected by the obscuration. So you miss it, you start to lose it rather quickly when you add the obscuration. The soft X-rays also get absorbed. The red is mostly isotropic, so essentially that's re-emission, so you see it. And yeah, and I think that covers pretty much everything. And that's why you get all these different SEDs. And this is what we tend to see, and that explains most of the systems that we see. Now, another consequence of that, which you probably notice here, is that in particular in X-rays, the ratio or the contrast with the host galaxy emission is very high. As I was saying before, normal galaxies don't emit much in X-rays, mostly from X-ray binaries and a little in a diffuse component from the quasars, but that's it. While AGNs are very luminous in X-rays. So turns out that X-rays, and that's how I started working on these, X-rays are a great way to study study growing black holes or studying the AGN population. A consequence of that is that while they're not completely unaffected by obscuration, obscuration can play a role as well. Now, something to keep in mind, the X-rays in AGN come from inverse Compton scattering. Essentially, we have a cloud that we call the corona, which essentially is a distributed population of relativistic electrons, mostly fully ionized gas, that upscatters the UV emission from the region. So this is emission that is coming from the very center, from very close to the black hole. And so because of that, it's affected by all the surrounding material. Again, this is an artistic representation, but you see that depending on what you assume for the geometry, again, which I promise not to talk about, but in many cases, you get most of the, let me start again. You get some of the emission affected by obscuration. And obscuration in X-rays is strongly wavelength dependent or energy dependent, if you will. Essentially, the soft X-ray emission, the emission at the lower energies, is more affected by obscuration, which you can see with this moving spectrum. While when you go to higher energies, unless you go to the very high end, the so-called Compton-thick sources, where you're essentially optically thick at all wavelengths, you're not very affected, right? So you need very high column densities in order to be affected by obscuration. And so with this idea in mind, turns out that if you want to study how black holes grow, studying them in X-rays is a good way to do it. Now, again, this is something that people have been doing for 40 years, something like that. People started doing that with things like balloons. Turns out that studying X-rays is hard. You cannot do it from the ground. The atmosphere, which is good for us, absorbs most of the X-ray. So we don't see X-rays in the ground, so which means that you need to put the observatories in space. The early work was done with balloons, essentially, when you have these very short limited missions. And this is how actually the X-ray background was discovered in the 60s, which but now obviously we have actual missions and space observatories like Chandrax and Newton and other that are studying X-rays all the time. So with these very early observations, people discovered the X-ray background, essentially a diffuse emission that seemed to be coming from our sky, and that had a very interesting spectral signature. It was, or still is very hard. It peaks at something like 20-30 kiloelectron volts. And obviously declines towards both lower and higher energies. And for many years, it was not clear at all where it's originated. And also sort of hypotheses about where it's coming from. Now, these were actually not the original, but close to the original one. This was from the 80s measurements with the Ezequiel satellite of the X-ray background. Now, of course, since then, basically every X-ray mission has measured the background. And now what we have is something like that. This is from a more recent competition by Nico Capelluti. And now this is basically, as I was saying, every X-ray mission, it's kind of a basic thing that you need to do is measuring the X-ray background. Now, when you do that, finally, we have a very nice, consistent picture where all the satellites agree and more or less confirm what we saw before, but a much better data, of course. And notice that now I use the word X-ray background in quotes, and the reason why I'm doing that is because, as opposed to, for example, the CMB, the X-ray background is not a real background when you can actually resolve it. When you take deeper observations, high resolution observations, you start to resolve it into individual point sources. And well, I'm going to mention that in a second, but the fraction that you resolve depends on frequency or energy, and obviously the properties, the sensitivity, and the spatial resolution of your observations. But essentially what this tells you is that the X-ray background is telling you about the average properties of the X-ray emitting population. You can break it into individual sources. And when you do that, the vast majority are AGN. Essentially, the X-ray background is an integral constraint on the X-ray on the AGN population. Or in turn, the X-ray background tells us about how the typical black hole grows. Right, so sort of connected with my original ideas. And again, this is not something new at all. This was first introduced by Roberto Setti and Walter back in 1989. This idea that you can use, and again, when it was first discovered, it was not clear at all how to explain the X-ray background, but this idea came that you can explain it by a combination of obscure and unobscure AGN. And why do you need that? Because essentially, if you remember the previous animation, the typical X-ray spectrum, the intrinsic X-ray spectrum, is flat in these units, which actually for many years was a problem, was a serious problem, because back in the 80s and 90s, basically unobscured AGNs were all that people knew about. About the quasars, called the quasars within X-ray. And they were flat in these units, yes.
Is the obscuration just dust?
So that's an interesting, essentially it's actually mostly gas. It's mostly ionized gas. We don't see it, so there are two, I wasn't planning to talk about it, but essentially there, no, because you can go into too much detail, but essentially it's a combination of continuum absorption from the gas plus ionization edges from different species, from different highly ionized species. And the combination of the two gives you the total absorption. And at least that is true at the Compton-thin level. When your emission becomes optically thin to the Compton emission, you become optically thick at all wavelength, and then at that point, the whole emission is suppressed. That's in 30 seconds an explanation that should take much longer than that. But yeah, no, that is very important for this, right? Because essentially what people realize is that if you take at that point, and again, back in the 80s and 90s when these ideas started, people didn't know much about obscure AGNs. We didn't know how many there were and how do they look like. But people realized that when you add absorption, which preferentially affects the soft X-rays, you can start to get something that looks more like the X-ray background. So the idea is that if you put the right mix of obscure and unobscure AGNs, you can explain the X-ray background, the spectral shape of the X-ray background. And again, these are the list of the people that were starting to do it. Actually, I kind of did that for my PhD thesis, not a long time ago. And people have been doing since, and with more refined models. But essentially, just feeding the X-ray background becomes a constraint of how much black hole grows. Right? This is sort of a zero-level test for all your AGN population synthesis models. Partly why we can do that is because now we are actually resolving, mostly thanks to Chandra and XMM, we are resolving the X-ray background. Now, one fundamental problem, and again, going back to obscuration, is that Chandra and XMM essentially work here at regions, they trace emission at less than 10 kiloelectron volts, which are still affected by obscuration, less than other wavelengths though, but they're still significantly affected by obscuration. But we didn't used to know much about the peak of the X-ray background. So the peak that, there you go. The peak that comes around something like 20 to 30 kilo electron volts, right? We didn't used to know much. And the reason why we didn't know much is because Chandra XMM works in this wavelength. So now that changed. I can present this other part. This was the biggest improvement in the last few years, thanks to new missions. First with missions like Integral or SwiftPath, which essentially were coded mass, so terrible resolutions, so basically several arc seconds, even at minute resolution, low sensitivities, but you can start to study AGNs or the peak of the X-ray background where even heavily obscure AGNs. And now, even more recently, in the last 10 years, we have NuSTAR, which is the first focusing hard X-ray mission. And essentially, we went from resolving only like 2% of the X-ray background in SwiftPath, in the peak of the X-ray background, to something like 35% of the X-ray background resolved directly, and even 70% when you stack Chandra sources. So essentially, if you take Chandra sources, you put them together, and you see how they look in NuSTAR, with the NuSTAR observation, you can explain something like 70% of the X-ray background. So then the challenge became how to incorporate that into our actual AGN population model. So essentially, what does this mean for black hole growth? And this was the work of Tanima Anana. She graduated a couple of years ago, a PhD student at Yale, working with both Meg and myself, who actually took all the information that we knew about the AGN populations, including the X-ray background, including the surveys coming from Chandra, XMM, and NuSTAR, put them all together and came up with a model, with an AGN population synthesis model that can explain the X-ray background. And turns out that she was able to do it, and she did it very well. This was a couple of years ago, and you can see that it passes the first test of explaining the spectral shape and intensity of the X-ray background, while at the same time explaining all the other properties of the AGN population. And essentially, I mean, there are many plots that actually were presented by Tanima, but this is probably one of the most interesting one. You can see that her model explains extremely well the fraction of the resolved background as a function of energy. Actually, the interesting thing is that this was not done, essentially, this was done independently before the actual observations came through. So the fact that we were able to explain so well the resolved fraction, I think is very important. And in addition to that, it fits all the number counts, the basic distribution, all the other properties as well. But again, that's probably all I wanted to say for now. The important thing, the other thing that how you turn that into understanding black hole growth is through the so-called the Sultan argument. Essentially, when you take the AGN emission, the AGN luminosity, you can turn that into a black hole accretion, an accretion rate. You can integrate that accretion rate, and therefore you should end up with the black hole mass density that is included. Again, this is not by any means a new idea. There's a beautiful paper, actually it's called the Sultan argument because of a paper by Sultan in '82, which actually presented that in it's a 1-2-page paper, which is beautiful, essentially showing the equation. This is the most modern version of the equation from Tanima, but essentially it all says that if you integrate the AGN luminosity, you should get the observed black hole mass density and its evolution. And turns out this is the most updated plot from Tanima's model, and you can see that indeed, you see, you can fit very well the observed space density at redshift 0 with the models. And essentially, the only free parameter is phi zeta, which is the efficiency, essentially how efficient you are, how efficient black holes are into turning black hole accretion into luminosity. That is the only free parameter, which is a normalization parameter in this plot. But yes.
Did I assume that the background is primarily being produced by nearby objects, or?
That's an interesting question. I didn't get to that, but yeah, basically, because it's an integral constraint and a flux constraint, most of the X-ray background is produced by sources at redshift less than 1. And typically the peak is at redshift between 0.5 and 1. So it's not the most local sources, but are not the redshift sources. You can compute what is the contribution from very high redshift sources and its conclusion.
Yes, flux, you're integrating with it.
Exactly. The reason is exactly that. That is a flux space. Such you're weighted by 1/d².
Yeah.
And therefore high redshift sources don't contribute that much, even though they can contribute a lot to black hole growth.
Right, and the volume is going as d³. It's, yeah.
Exactly. And that's why I was saying that feeding the X-ray background is a very important constraint, but it's not, it doesn't tell you the whole story. And that's something that you need to keep in. Thank you for pointing it out, because it's very, very relevant for this. And that's why, well, I didn't talk about it because this is only half of my talk, but essentially you need to combine it with all these different tests, with vivo study, with number counts, with distribution, and so on, which actually Tonima did on her work. And models
densities from the flux, or are they densities?
Okay, no, in this plot, you mean?
Yeah.
In this plot, they're actually black hole mass density.
And how are the points?
The observed data points, they come from integrating essentially, it's kind of cheating, right? Because we only have accurate black hole masses for very few sources, but we have scaling relations, right? So you can take the galaxy population, you measure what are the black hole masses, you measure the black hole densities, you can integrate those. And that's how you get the integrated black hole mass density at a function of redshift.
But is the density taken from X-ray data, or is it from like stellar kinematics?
No, it's completely independent from X-ray. It's from,
Gotcha.
It's essentially from the Sloan, from turning any kind of correlation, any kind of scaling relation that you want to turn the galaxy properties, the galaxy luminosity, for example, into a black hole. And then you integrate that. So it's completely independent of the X-ray. Which in a way is nice, right? Because that's why it's not circular at all. And actually, that's an interesting point. There's no reason for this to be true, right? But for among other things, so black holes can grow without emitting a lot of radiation. What the Sultan argument, actually, that's a great introduction for my next slide. So thank you. What the Sultan argument tells you, right, is that if you count the emission, the luminosity from AGN, you account for all the black hole, for all the massive black holes. And that is not obvious at all, right? Because there are other ways in which black holes can grow without emitting radiation. So actually coming back to this, so then the question is, after we've done all that, should we stop there, right? Like, do we know everything? Do we know how black holes grow and how they got their masses? And that's the end of the story. Should I finish all this research? Should I find something else to do at this point? Obviously, the answer is not quite like that, right? Obviously not that. Essentially, even though it is true that the Sultan argument says that you can account for the observed black hole density or the black hole mass density, there's still room for about 2 times more black hole growth that is still unaccounted. And that is very significant, and I'm going to describe in a second why we believe this is important. Essentially, there's no reason to believe that the amount of accretion, the amount of black hole growth that we are missing is the same as the one that we found. So it's not just extrapolating AGN luminosity, and we will get the total black hole mass, and that will be the end of the story. It's probably more interesting than that. And why do we believe that is something like that? First, it has to do with something that I didn't mention until now, but is fundamental, and it's that black hole growth is highly episodic. Black hole in the Milky Way is not growing right now. It has all the ingredients, but it's not growing. So for some reason, you need for something to happen for the black hole to grow. You need a triggering mechanism. You have episodes of black hole growth, even if you have all the ingredients. Question then, what triggers this episode of black hole growth? And it all comes down to how do you feed a black hole, and essentially how do you make sure that the gas, essentially the material that is mostly gas that is accreted by the black hole, loses its angular momentum so that it can be accreted by the black hole. Essentially two routes to do it, which is what is described here. One is through internal processes, essentially some sort of dynamical instabilities. It can be bars, for example, it can be the minor mergers, it can be some stochastic processes that happen inside the galaxy, or it can be external. And by external, it can be major mergers, major galaxy mergers. And this has been debated, this is still heavily debated, which one is the most important mechanism, which one is the one driving most of the black hole growth and so on. But this is when it can get exciting, get interesting, because when we start talking about the major galaxy mergers, it turns out that but you can connect again, going back to this to the introduction, you can connect the black hole growth to the properties of the galaxy. Essentially through the major mergers, these very specific phases where you have very high star formation rate, when you change the morphology and so on, you can connect black hole growth to galaxy evolution in a more direct way. But it's far from obvious too how it happened, even though both simulations and observations at low relative essentially predict that some connection like that happened. And in fact, some of our early work that we did was more than a decade ago now, we found that indeed you can link the major galaxy mergers to black hole growth in this sort of evolutionary scenario where we first trigger a heavily obscured quasar. Essentially, you're completely surrounded by gas and dust, you're completely obscured first, and then you reveal an unobscured AGN. Now, again, this is something we've been studying for several years, and that people have been studied by many years, and probably, still less controversial now, but people should talk about it. I think it's very clear that now we can link, in particular, the highest luminosity sources to major galaxy mergers. So essentially, when you look at the host galaxies of the highest luminosity sources, which in terms of the highest accretion rate, they all seem to be connected to major mergers, to recent major mergers, right? And this is from our work a decade ago, but people have been doing that for many years now. In many ways, a consequence of this scenario is a lot of what is driving this controversy is that when you look at your typical AGN, it has nothing to do with mergers. It's triggered by internal processes, again, dynamical instabilities or the other one. So something like 90% of your AGN by number are triggered internally. So it's only 10% of the AGN, but when you integrate, and of course it's more complicated than that, but that's a good ballpark number. It's something like 10% are triggered by. But because they're the highest luminosity, they can account for something like 60% of the total black hole growth. And it seems like this is essentially, and going back to my previous point, this is the part that we are missing. And we are missing because essentially we are, a consequence of this scenario is that the first part of that, or at least the early stages, are highly obscure. And essentially, I think we are coming to a scenario where we have all this zoology of AGNs and quasars and super galaxies and all these different names that people gave for these sources, but it seems like this early unification diagram only works for the low luminosity system, so the slowest growing black holes. While at the highest luminosities, we have this evolutionary scenario, and essentially this over here is the part that we are missing. This is essentially the population of growing black holes that we are missing. Then what evidence have we obtained? So again, thanks to NuSTAR, essentially in the last few years, how do we proceed? How do we make progress in studying this population? And so, for example, we now take, again, I'm not going to get into much detail, but doing a study of the AGN fraction as in measures, we see that essentially in confirmation of this scenario, you find a much higher AGN fraction, so fraction of galaxies hosting AGN in the late measured stages. So essentially, when the two nuclei are closer together, is when you're more likely to find AGN. Not only that, but also these AGN are, as we expected, are in general much more obscure than the general population of AGN. And in fact, this is a plot that Claudio Ricci put together. Claudio was a postdoc on our group, now he's a faculty at University in Chile, but he essentially using both archival and our own NuSTAR observations of AGN emergers, he found that the fraction of Compton-thick AGNs increases rapidly with separation, with nuclear separation. So essentially, when the two nuclei are closer together, that's when you have the highest obscuration. This again is very interesting because that's exactly what we were expecting to find. This data point is probably highly affected by incompleteness, so it's probably much higher than that, but you get very high values. You get that at nuclear separations of about 1 kiloparsec, you get 80% of the sources are Compton-thick. It's highly unusual. So this again goes in the right direction, and basically that comes to the last part of my talk, which is what I'm working on now, which is in trying to understand essentially this missing population, these last stages. So when the two nuclei are closer to each other and most likely the most obscure. Why do we care about that? Is because it's in these later stages of lack of growth, that's where we think that the most intense, or at least what simulation tells us, is that everything is taking place. Right? When you have these very high star formation peaks, when everything is obscure, and you have significant black hole growth as well. So this is something that we've been studying for a few years. I think something interesting that came is that we do have a large number. This is essentially our parent population. So we started from sources that were selected from the Swift path samples, essentially in X-rays. You know that you have an AGN, but when you look in detail, and these look pretty much like normal galaxies, maybe you see some tidal veins or something, but they look exactly what you expect for late stage mergers. You see that indeed they have two nuclei. They seem to have two nuclei, and they seem to be very obscure as well. So this is our parent population that we study in more detail. Just a few slides on a couple of sources that we've studied. One of them is NGC 6240. For the people that follow this field, is very famous. So is a so-called archetypical dual AGN in that it has two growing black holes at the same time. It's also a very active galaxy. It's at the Lerg level, so it's almost within the boundary between a Lerg and a Euler. It has a very high star formation rates, more than 100 solar masses per year, which for the local universe is very significant. And it also contains two very massive black holes, about 10 to the 9 solar masses each. When you look at this system, it's a mess. You have, again, it's the beauty of this system, right? You have everything happening at the same time. So you have intense star formation, you have very rapid black hole growth, and you have both of them happening at the same time. You're ionizing the gas around it, so you have part of the ionization happening due to the star formation, part due to the AGN, and you can try to separate the two. And both of them combined are similar to the star formation rate in the system. So make it very exciting. Again, these are very exciting times for the galaxy. What we added to this picture is the ALMA. ALMA observations trace the molecular gas. In particular, we were using the CO as a tracer of the molecular gas. And what we studied is the molecular gas in the region surrounding both of these black holes. You can see in this case, the two black holes are separated by about 1 parsec. These were the existing observations before ALMA of the molecular gas in 6240. The resolution is about 100 seconds, so the gas is marginally resolved, and you can see that is most of them, they're significant. There's something like 10 to the 9 solar masses of molecular gas in the region, mostly in between the two nuclei. Now, this is how it looked like before ALMA. This is how it looks with ALMA. In cycle 4, we increased the spatial resolution by a factor of 10, which people do this but more than the wow factor is that you can actually study, you can start to study what are the dynamics and what is going on in the system and how essentially this is the molecular gas that is feeding both black holes simultaneously and what it's doing. And what we see is actually an area did that for us a couple of years ago when we released this data. So you can see that now this is the combining ALMA and HST observations. So we see the two black holes, again separated by about 1 parsec. Most of the gas is in between and it's forming this string connecting the two nuclei. This is a bit more complicated to study because it's not actually a 3-dimensional, it's 2-dimensional plus velocity. So what we see, I'm going to play the dimensions to show this part because what we see this separated clump of material. Let me see if I can do it here. I'm going to show that part here. So we have the two nuclei and the filament connecting the two. And we see this is actually an outflow of material moving at something like 500 kilometers per second. In something, well, I'm going to show it in a second, but it's something like 10% of the total molecular gas in that flow. But now, thanks to ALMA, we are starting to resolve, we are actually resolving the sphere of influence of each black hole and what is the gas doing. So essentially, we know that essentially everything that is inside of each of this white circle will end up falling into the black hole and end up feeding the black hole. We actually found this high velocity structure, which if you turn that into an outflow rate, which again, you have to be careful because it's actually not really outflowing. This is, even though it's moving at 500 kilometers per second, we think that it doesn't reach completely the escape velocity of the system, so it's not clear that it will actually leave the galaxy. But if you turn it into an outflow rate, it's something like 4,000 solar masses per year, which is of course huge. It's very, very significant. And again, it's an example of how black hole growth, if we think that this is all driven by black hole growth, can affect the rest of the galaxy. And then just to finish, the final example that we're working on, which we're very excited about because this one is actually the dual AGN, so two black holes growing simultaneously at the smallest nuclear separation of something like 0.3 arcsecond, we translate the derivative of this source into 200 parsecs. So in this case, the two black holes are only separated by 200 parsecs. And you can see this is the ground-based imaging. This is from Vegas. It looks again like a otherwise very boring galaxy, except that it does have tidal tails. It's funny, the tidal tails were there for 20 years and were hard to see. Now they're obvious, right? But for many years, people classify it just as a normal galaxy. When you look into much more detail with a combination of HST imaging, with KEK, AO, and BLT with AO with MUSE, you do see 2-point sources in the center. When you put them in the BBG diagram, they are definitely in the AGN region. So we think that this is very clear dual AGN. So essentially, in each of these nuclei, you have a global dipole. The final confirmation for that came from ALMA, from our observation, from our program, from observations that were taken, started last year and they were finished only a couple of months ago. But essentially, with ALMA, we're tracing both the CO again and the continuum, but at very high spatial resolution of something like 0.5 arcseconds. So we are clearly resolving this system with only about 2 hours observations. And you can see this is the continuum emission, the submillimeter, actually the millimeter continuum emission. And in both nuclei, we see unresolved emission that is consistent with essentially a non-thermal, most likely synchrotron emission with a very far spectral index coming from each of the nuclei independently. So this combined with everything else is what gives us confirmation that this is a dual AGN. More importantly, we can actually, we can measure the flux in the other side. And now there's a very clear correlation between the millimeter flux or the millimeter luminosity and the X-ray luminosity. So essentially, we now think that sub-millimeter continuum is a great way to find AGN in general, but it's a great way to find dual AGN as well that were previously impossible to find, basically because it's unaffected by obscuration and because ALMA provides the highest resolution. So the combination of the two is what makes this a great tool to find the AGN. So based on that, and of course I won't be able to show results because the program was just approved and the observations will be taken next year, but we have a sample of 12 visually selected post-mergers that we are going to follow up with ALMA, essentially following this idea to use the sub-millimeter continuum to see whether they actually host dual AGNs as well. And essentially, the fundamental question is how often does this happen? And again, how much black hole growth you can hide in this last merger stage. That is a fundamental idea. I'm not going to claim that we can solve it with this program, but it's definitely a good start. So far, we have 2 or 3 sources and we are going to target 12 of them. And finally, in the last slide, why do we care about it? It's because, well, there are many reasons why you care, but another one which I find very interesting is because essentially these systems are essentially the progenitors of the parent population for gravitational wave events. So in something like 10 to 15 years, when we have something like LISA, we should be able to find gravitational wave events at a frequency that we don't know, that actually is part of the experiment. And essentially, they will come from systems like that. Not immediately, because if the simulations are right, it will take a giga year for this thing to collapse. But essentially, this is the power, the parent population that will generate the gravitational wave. So I like to finish. So I think we are starting to understand and have a complete census finally of the supermassive black hole population, but we do still need to understand this final frontier, the heavily obscure phases that happen at the last stages of a merger where you can hide significant black hole growth still. And luckily now we have ALMA, in particular the ALMA continuum. I think it's a starts finding this and understanding and studying the system and hoping we can do that in the next few years. And hopefully in a decade or so, we can study these events with Lisa. So with that, I would like to finish. So thank you very much.
Before we do questions, there's like 2 more slots open for dinner. So if you'd like to join us for that, please do. And then I think there's also like a handful of meeting times tomorrow where we went to Houston. Questions?
I'm curious about the object you were showing. Is there something that tipped you off that there was here, or you just happened upon it in X-ray data?
That's an interesting question. So actually, here. It started from this sample. Actually, this one over here. So basically, we have, and this is very rusty. We are looking for things that look like they have some mergers.
Data or
In the optical, mostly in the optical. We are looking for something like tidal state, tidal depth, or anything. So something I didn't talk about is how do we actually become more serious about it, right? Because so this is starting from the Swift path sample. The Swift path all sky sample is something like 1,000 sources selected in half-Earth rays, but with turbo spatial resolution. So you know that there's one AGN. We don't know whether there are 2 or that's the next step. So that's how we started, and there are about 1,000 sources. So we actually look by eye, and we try to find it.
so you have your catalog of like 1,000 X-ray sources, and you're just kind of characterizing all of them, and some of them happen to be.
And we look at them, the ones that look like post-mergers. And then we do the next step where we take tech imaging with AO. Now we are doing it with Gemini as well, and with ASOI. We are doing imaging at higher resolutions to see if they're consistent with having nuclei. And then we add the spectroscopy with luminous, for example, and so on. And in the future, so this is, for example, the parent sample for the ALMA program. Now, this is not how we want to do it in the future. So something I don't talk about. Obviously, there are large galaxy surveys coming, and ideally we can do this in an automatic way. That doesn't imply having the images by eye. Hopefully, we can do maybe some AI tools to identify them. So we have a student working on that, whether we can use AI to train computers to find post-merger features automatically in imaging surveys. And that's combined with the next generation imaging surveys like LSST and all, is what will generate samples of thousands and tens of thousands of these. This is how we do it with more factory level. Right now we are doing it fine to do it for 1,000, but that's sort of the limit we can do by
Yes, so following up, I mean, thinking, so the last slide before was inspiring. It'll take about 1 billion years for these things to merge. And the phase you're looking at, what starburst phase, maybe it's 100 million years, 50 million years. So for one of these 20 things that are already emerging have gone through this stage, they're on the way in. And so I'm thinking, how do you find those? They're not going to be accreting much. Look for like spectroscopic luminary.
It's a fundamental, yeah, that is a great question. Thank you. How do you do it, right? We're basically pushing the limit, right? So 60 to 40 sits around here. The kiloparsec UGC 4211 is here. This is actually, this was found in radio only, and we cannot follow it up. The separation is on the level of milliarc second. So essentially in the radio it looks from VLBI. Or
So VLBI would.
VLBI will look. The problem with this system is that you cannot follow it up in any other way.
Yeah.
So essentially we are pushing the limit here, but it's unclear how you go here. And right now we don't have The most honest answer to give you, that I can give you is we don't have anything yet. So we are pushing the limit on getting here. And that is important because this is the part where essentially, and again, you give this or the theoretical models of how black holes end up merging. Essentially, you again need to get rid of the angular momentum. And essentially here you do it through stars. Essentially stars come into the system, take the angular momentum and leave out. So this is the regime where we are now. And this is the best we can do.
Well, you're right for imaging, that's right. But that's not how we found the first exoplanets. We found them with radio velocities. So couldn't you look at unresolved nuclei and look for double line binaries basically with huge velocities, I guess, right?
And you can, and you do, and people do that. The problem with that is confirming that this is the case, that you actually have a duality. For example, you can have features in the accretion disk that will look exactly like that.
Oh, yeah.
Right? And because of that, the beauty of this is that I can show you 2 point sources.
Right.
And I can do a resolve spectroscopy in each of the nuclei and all that. The problem when you live around here, which is essentially what people are doing, is that so far you only have candidates. Because there can be other factors, like for example, instabilities in the accretion disk that will generate the same signal. And you cannot tell them apart. People do that a lot.
Okay, what's the based off of merger? Is there a bias in there? I think you want the run. It's like you're kind of wagging the dog, you know. Like, is there a hope to do that? Get a picture that kind of makes sense.
I mean, that's what I would love to do in the next 10 years, right? So essentially, how do you go with the, when you go butterfly peaking, right? When the forest of people that study, how do you go from studying individual systems to a population study? Essentially, that's what we are dealing with right now. And it's kind of connected to your question, right? How do we go from individual examples that are cool, pretty pictures and all that, to actually understanding something about the black hole population, black hole growth. And that is the challenge. And in order to do that, we need a systematic way with larger statistical samples, and fundamentally we need to understand the systematic. So actually, I have a beginning PhD student working on precisely trying to answer that question. She's just starting, so I cannot. But this is one of the goals of her PhD thesis. So essentially, once you fold in this individual system, and more than the system that you find, let's give you the rate. You fold in all the systematics, all the biases, all the different selection effects. You fold it into your Billion population synthesis, and you bring back what does it mean for black hole growth. It's not easy at all, actually. To be honest, right now I don't think we have the answer at all, which is, if we keep going in this direction, if we have larger and larger samples, I do believe ALMA, this continuum emission is the way to go. Is the way we need larger samples, and again, the fact that it's not affected by obscuration and that it reaches very high spatial resolution, tells us that this is the way. Again, have cleaner samples, larger number of sources, and then we can fall into our AGM population models, running into how much black hole growth in this system, which is sort of crossing the line.
So if you don't have to follow, black hole growth happens like quasar.
No, well, that question. The problem is we don't know yet, right? Yeah. Because essentially, black hole growth, what happening what the subgrid, right? Essentially, all the if you want at the same time to simulate the whole merger, right, in scales of tens of kiloparsecs or even larger, and at the same time, we saw black hole growth, which happening in parsecs or even sub-parsec scales. You cannot do that. You end up making very rough assumptions about what the accretion, for example, and not even the gas dynamics. This is the relevant scales I'm not fully understand, and the simulations don't tell you that. So that's the beauty of that. So basically, in this case, it's the other way around. We are informing simulations because we are in a regime where simulations don't have the resolutions to make accurate predictions. They essentially put recipes in, and then they, like the Hopkins and the fire simulations and all that, essentially what they recover is what they put in. But they're not resolving it from fundamental physics. So that's why it's important to do it. We're not resolving them either, but by doing this population study, we're trying to stop understanding. For example, things like that. When a galaxy merger takes like a gigayear. And we know that the black hole growth stage is only
We're at the hour, so let's think of again.
Might as well.
Also, also practical.
Yeah, I'm just a star. Do you wanna? Grabs him.
We're talking about
I don't know if they're-